So good morning, everyone. It's nice to be in the ICTS campus. I think all of you are impressed by the wonderful, beautiful campus. Somdatta requested me to give a sort of overview of type of things we do, and so I'll go very slowly, starting with my background actually, in case you haven't read it from there already. So I was born and brought up in a small town called Darjeeling, which is of course famous for its tea and its very high mountains and beautiful schools. I used to walk past this Capitol Hill every day to my school, which was on the other side of the hill. So I went to St. Joseph's, which is one of the Catholic schools. And then I went to Mount Hermon School, which is a Protestant school actually. So I had a taste of both. Then I was in Scottish Church College in Calcutta. And Tushar was my classmate there. And we used to stay in the similar hostels adjacent to each other. Then I did my master's from University of Calcutta Science College, Azabazar. And it happens that, at least 50% of the Indian physicists come from there. So they say that if you want to study physics, you should learn Bengali first and then you study physics, because in every part of the country you will go, you'll meet Bengali physicists. I believe it's so for economics also. And so it becomes quite difficult for us to choose speakers who are not Bengalis, and we had to make an effort to actually bring people from all over. But it's wonderful that you have come. I did my PhD at Saha Institute of Nuclear Physics. And then I was a faculty in France, where I completed my habilitation from University Pierre Marie Curie. For my postdoc, I had gone to Helsinki University of Technology, and there I survived temperatures of minus 36 degrees Celsius. And then for a time I was in Brookhaven National Lab, which is more famous for its accelerator. This is the relativistic heavy ion collider. This is 15-mile, 10-mile radius, huge campus. And then I came to Banaras Hindu University, which is again one of the largest universities in Asia, with 1,300-acre campus actually, which is built in the shape of a rising sun. So you see these are the rays of suns coming from the central office, and then the departments, and then the quarters, and then the hostels. Here I survived plus 48 degrees Celsius with 14 hours of power cut. So it's anything in between minus 36 and plus 48, I'm very comfortable. Then I went to France. I was offered a permanent position in École Centrale Paris. And so it's very famous for mechanical engineering, automobile, hydrodynamics and things. So Gustave Eiffel was an ex-student of theirs, and all the French car companies, Citroën, Peugeot, Renault, they're all ex-students of these schools. And then in 2014, I joined JNU and to start the Center for Complex Systems. And so it's in the School of Computational and Integrative Sciences. And that's why I want to, give you a few things of what we mean by integrative science of complex systems. So what is science? Of course, science is a knowledge or a system of knowledge covering general truths or operation of general laws, especially as obtained and tested through scientific method. And we really actually say what is a scientific method. So what qualifies to be called as science and what doesn't qualify to be called as science. And we are all trained in this way, and which is very different from what how social scientists approach. And you'll see the difference actually in these approaches. Now, traditionally, science in physics, for example, we've been following a path of what is called reductionism. And so I can give you an example. For example, if I ask you, what are we made up of? So we're all made up of cells, tissues, and all that. And so this is in the realm of biology, and you study these, right? And then we ask, what are these cells made up of? And of course, they have a structure, and you see that you have a DNA which carries all the information, and we are already in the realm of biochemistry, chemistry. Now, if I go and ask, what is the DNA made up of course, they are made up of different atoms, which are chemicals. And each of these atoms also has a structure, electrons, protons, neutrons. And then I can go and ask, what are these neutrons and protons made up of? So we are in the realm of physics. And then you can see that there are two types of particles in the universe. Some are called fermions, and the others are called bosons. And there are no third type. So these are the two types of particles that we see. And anything which forms matter normally fall under this. And all the interactions or forces are bosons. Now, the properties are given. Now, if I know all the properties of these particles, the matter, which form matter, or the interactions which are mediated by particles called bosons, can I explain the working of the whole universe? Okay. Now, certain things we can, the other things we cannot. And so there is a limit of reductionism, and which was wonderfully captured by one of the Nobel laureates in physics, Phil W. Anderson. And he had a wonderful paper in Science in 1972, which was entitled More is Different. And then he's mentioned in that article that there is a hierarchy, like I was going, from particle physics, many body physics, then chemistry, molecular biology, cellular biology, physiology, psychology, and social sciences. But each science obeys the laws of the science that precedes it in endeavor. But this does not imply that one science is just an applied version of the other. Okay? Because at every level, new laws, new concepts, and new generalizations are necessary. Okay? And so in my domain, I apply physics into chemistry, computer science, biology, economics, and sociology. I apply maths. And so you find that there is an integrative approach, and that's what we call integrative science. Okay? Now, often it happens in scientific research that we say we will solve this problem using science, then theorized result is we have solved the problem, but actually the problem is much more complex than we first thought. So it often happens that even the simplest of things cannot be explained, and we build models and try to capture the essential features, but the real system is much more difficult and more complex. I have a small group which we called etc. Research Laboratory, because we do experimental, theoretical, and computational research. And I'm trained as a statistical physicist, but I work on all these different fields, and my students and postdocs come from different subjects. So she's a statistical physicist, a computer scientist, nanomaterial scientist, computer science, electronic science, complex systems, and physics. Okay, and in our lab itself, we do a lot of interdisciplinary applications. And so today I want to talk on complex systems. Again, if you just go and check Wikipedia, you will find that, examples of complex systems and the various approaches to study complex systems. Now, we are used to studying macroscopic objects with large number of particles in physics. So typically, suppose, you take a bottle of water, this bottle of water would contain about, 10 to the power of 23 molecules of water, which is called the Avogadro number. And the thing is, all the structure of the water molecules are same. And so what happens in physics, we often, write what is called the Hamiltonian of the system. And then we try to describe the properties and dynamics in terms of this Hamiltonian. And unfortunately for these complex systems, these are constituted of particles which can be various in shapes, in forms, in types. So form as a room full of people like this would be actually a complex system, because each one of us are very unique and different from each other, and the interactions between us are not known. And so I would not be able to write a Hamiltonian and tell the properties of the system in terms of the Hamiltonian. So what happens is, when I study one person in isolation, it is very different from how he would behave collectively. And so when you have a collection of such constituent particles, the collective behavior shows new emergent properties, and the system is nonlinear. There are other features like spontaneous ordering, sometimes self-organization, and various other things, okay? And that's make the things more interesting, at the same time more difficult. In today's talk, I will be actually focusing on these two places. One is agent-based modeling, which deals with collective behavior, and game theoretical models, okay? Now, this research, the tools of physics that we applied to solving problems in economics and finance, we call it econophysics. And when we solve problems in sociology, then we call it sociophysics. We've had several books and textbooks on that. Most of my work is actually on this income and wealth distributions. And another part has been modeling limit order books, which is stock markets. We've been holding regular meetings in econophysics, firstly in Kolkata and then in Delhi, and several other books, edited books are there. If anybody is interested, I can share the content with you. The last two meetings were held in Delhi, and we have this econophysics and sociophysics, so a lot of articles contributed by experts. And there's a wonderful book by Parangomadi, who's sitting there, along with Professor Vikas Chakraborty, on social physics. This was published by Oxford, and it's a wonderful book which I advise you to have a look. So I wanted to give a little bit of overview before coming to my actual topic. So we say data science in sociology. So we study problems like, how languages diffuse in space and time, okay? And this we actually studied the Mazatec languages in the southeast part of Mexico. And this is actually called the Miguel Alemán Dam. And you have a group of languages. There are 12 cities. And what we try to do is, the same words are spoken slightly different in each of these cities. And we know that happens in any of the languages. So I am from Bengal. The people in Midnapur, which is southern part of Bengal, would pronounce words differently from those who are from another district called Badwan or Dinajpur or anything. And so if I am a good expert in Bengali, I would be actually able to point out that he or she comes from that part of Bengal. And I believe that's true for all Indian languages, Hindi, Kannada, or any other thing, right? Now, what we do is we look at these languages, we convert them into international phonetic alphabet. So each of these sounds are converted into international phonetic alphabet. And then what we do, we calculate what is called the Levenshtein distance, okay? The Levenshtein distance gives you the distance between two strings, okay? And so, for example, these two gentlemen who are sitting in front, their names are Ashish and Adarsh. And if I would like to calculate the Levenshtein distance between them, these would be actually the number of insertions, deletions, or substitutions I have to make in order to, the two strings are same. So you will see that I would have to make 3 changes so that those two strings would look same, and the Levenshtein distance between them is equal to 3. And so in this way, I can actually calculate the Levenshtein distance between all the words and take average over them to find these distance matrix. And once I have a distance matrix, I can use several machines.
Have the number of alphabets same?
No, if they are different, I will have to make insertions also, right? Yeah.
How did you get to that?
This was done by my French linguist friend Jean-Léon Léonard. He's actually a linguist who works in Paris, and he did a survey of this area. So he gave, that was a project by the European Union, where he went and did a survey for a very long 2 years period in Mexico and collected the data.
Pick up words which mean the same.
Which mean the same, but they are pronounced slightly different in each of these languages. And you get a distance matrix, and then you draw a network, with a threshold or a multidimensional scaling map to show how similar those dialects are. And you can see that these are similar and these are similar to each other, but then we found that there is a difference between this and there, okay? There's a strong similarity, though they are far apart. And then we understood that, there was a dam built which displaced the people from there, and they had similar profession here, so they actually migrated first. So this is how we construct what is called the ethnohistory of the languages. So it's called ethnohistory. Yes. Yes.
So in this example,
Yeah.
just to be sure,
Yeah.
here is 2 different words.
So what?
What you were talking about here is that the same word, let's say others,
Yeah.
is spoken by various people
Right.
in various places.
Yeah. So they might pronounce it like.
Looking at the distances between those pronunciations.
Yeah. So what we do is we convert it into international phonetic alphabet. So suppose somebody says Adarsh and somebody in Bengali says Adorsho. It will be slightly different. So they will record it in international phonetic alphabet and then use the Levenshtein distance actually. Okay. Right. Then we also study different social and antisocial phenomena like ethnic conflicts, human rights violations, terrorist attacks. So we have a huge collection of spatio-temporal data. And from there, I can construct networks. So if 2 actors, actor 1 and actor 2, are engaged in an ethnic conflict, I would draw a link between them, and in this way the network would grow. And there would be obviously some nodes which would be very big because they engaged in conflicts very frequently, and the edges between them, if 2 partners engaged in frequent conflicts, the edge is larger. And then you can use several algorithms in physics and computer science to find out, what is the backbone or which forms the most important or more central nodes and edges. And you can also use machine learning tools to actually predict, how they will grow and all such things. Okay.
How
Yes.
do you define
centrality?
Certainly, so this one was used to be using like disparity filter, but in networks you can use eigenvector centrality or.
No, but what is the meaning? Because eigenvector in this case, it was basically the question is which centrality is making sense.
That's
in
right.
Kind of complex network.
Right. So here we didn't use any centrality measures. We used what is called a disparity filter, which was proposed by Alessandro Vespignani, and there's a PNS paper on that. And so you can find out this and study in details how these backbones and all propagate.
Gautam from TCS?
This was Gautam from TCS. Then I will be talking this in more details on Wednesday. So I just wanted to tell that we also apply network theory to different features of the financial market. And also we use what is called the random matrix theory and all these tools from physics to identify and crashes and study the properties of the market near the financial market crashes. So this I will talk on Wednesday. Okay. And now let me come back to the socioeconomic inequalities and the kinetic exchange models which we use to frame that. So you know that income, wealth, consumption, expenditure, social rights, everywhere you'll find a sort of a inequality. And the questions that we are asking as physicists, how are these income, wealth, consumption distributed, or what are the forms of distributions, and are they universal or they depend on the specific conditions of a country, and how can we model these distributions and such questions, okay? Now, it's known among social scientists that societies which are equal often perform better, and there have been several books, and they study different variables like physical health, mental health, drug abuse, education, imprisonment, obesity, and many other things, and to measure the performance of societies. And they find that in average, even though a society may be richer than another society, if the inequality is less, then they perform better. And that's why, starting from religious leaders, they say that inequality is a social evil, to political leaders, Manmohan Singh giving a statement about a week back that rising inequality should be a concern. So you will see that, this problem of inequality actually is at the base of economics, and, many people actually study this very seriously. And in India, even though we have been having a very rapid growth, the income disparity between the rich and poor is increasing rapidly, which is again a concern for economists. So one feature that was observed, starting with a social scientist from Italy, that was Vilfredo Pareto, at the end of the 19th century, and he published a paper which said he measured the wealth in different European countries and found that there is always a tail which goes as a power law, and this exponent is now called Pareto exponent in his honor, and it varies slightly, but then it is always a tail that you see. So you'll see that if you analyze even modern data like in the 90s and the 2000s, everywhere you'll find a bulk followed by a tail. So this is the tail which is blowed up here. And in the US, in Japan, in UK, in every other country, you'll find similar features. And that's what interests physicists, that how do these universal features come? So there is always a bulk, a log normal or gamma distribution, followed by a Pareto tail. And so more data will show you again that there is a crossover, after which this becomes a Pareto tail. And we formulated in beginning 2000 a very simple model inspired from physics, kinetic theory of gases, and we call them kinetic exchange models. Now, most of the people who have studied physics, especially in Calcutta University, we've all studied this book, Treatise on Heat, written by two famous physicists, Meghnad Saha and B.N. Srivastav. And in one of their pages in the book, they had actually left it as an exercise for students. They proposed that, the distribution would be like this, and they said that you should find out why it will be like that, okay? They didn't give any explanation, and they asked the students that you should be able to figure that out. So very many decades later, we actually worked out. So this is a model which is studied in physics, and it's called kinetic theory of gases. So where we take, a closed system, and where we have filled up with gas molecules, which are undergoing random collisions with each other. So you can take any two particles, I and J, and they come with certain energy. Okay, so I and J come with certain energy, and I call them xi, xj, and they, after collision, they go away with another thing, xi prime and xj prime, okay? At every step, xi plus xj is conserved, so xi plus xj is equal to xi prime plus xj prime. And the total, which is summation of xi, which is capital X, is also conserved, and the number of particles is also conserved, okay? Now, if I have such a system, and I ask, what is the distribution of this energy? Then the answer is known. It was formulated by, it was first proved by Maxwell, Boltzmann, Gibbs, all independently, that it follows what is called a Gibbs-Boltzmann distribution, okay? And this T is nothing but the average energy of the system, which we call temperature, okay? So even in this room, you would have molecules which are undergoing collisions, and then you have a certain temperature, T, which is nothing but the average energy of the gas molecules. Now, instead of particles, if we have agents, okay, so we replace them by agents, and I shut the door, and I say that no one is allowed to go out, no one is allowed to come in, and we all have some money in the pocket, and we either do some trade or we do some exchange of services and we get paid. So what happens in the form of money, some money flows from my pocket to yours or your pocket to mine, and that would basically be an exchange of money. So if I'm looking only the money plane, I forget the commodities or the services exchange, then I would expect you'll get a distribution like this, okay? Now, you might say that, oh, this is too simplistic a model, and we agree that this is too idealized a system. And for example, we can make it further complicated by introducing what we call savings. So it's known in economics that, every society has a marginal propensity of saving, which is like a fraction between 0 and 1, and everybody saves a certain percentage. So let us assume, for example, in this room, we have a constant saving paper, yes?
I just want to understand, what is the law behind the exchange? How you determine
just
the amount of that you are giving to me?
Randomly, and we just split it randomly.
Randomly,
Yeah.
according to a uniform law.
Yeah. Now, suppose I start saving a fraction. So you have money X, you would save this. I have money XJ, I would save this. So the amount of money available for exchange would become this, right? And then what I do is I split a small part. This is a random, which is drawn from a uniform random distribution. So I had lambda xi, you had lambda xj, and so this side becomes my xi prime and xj prime. And this is the dynamical equation which we now start simulating. Now you will see that xi prime and xj prime, if I sum, will still be equal to xi plus xj. So every step there is a conservation and everything remains same, except now that lambda is a small fraction between 0 and 1. If lambda goes to 0, then I get back this model where there is no saving and you would expect a exponential decay. Now when you simulate this, you will find, starting from any initial distribution, you will always land up with some distributions which are stationary distributions and are given by what is called a gamma distribution, okay? And what we actually have is a temperature which is related to the dimension of the system, and this dimension is actually a function of this lambda. So in real space, when we actually have gas molecules colliding, the spatial dimension can only be integral, n equal to 1, n equal to 2, n equal to 3. But in this case, the lambda actually tunes the dimensionality, and it can be any fraction between 0 and infinity, okay? So that is what we call an effective dimension, and you can actually connect the lambda to this dimension using this formula. Okay, so this was a model which we had proposed in 2000, and then there have been several works. So what we do is these all have exponential tails because they have this gamma distribution. Now, yes?
Actually, say you're in the gaseous state.
Yeah.
Molecules are colliding very rapidly.
Yeah.
But if we look at the transaction pattern of
Yeah. Yeah.
so after some time that gets a particular value. So
That's right.
every day I'm going to a particular shop and purchasing something, so the money is flowing in a particular way.
True.
So,
So we
how
will.
long?
Yeah, so I understand. You mean to say that, it doesn't happen randomly,
Yeah.
right? So first assumption is let's take if it happens randomly, and then I'll show you how we can modify it. Okay, yes.
Another question. So you have a linear system.
Yeah.
So which you can capture through a differential equation.
Right.
And you know that it will converge, I guess, if lambda is small enough.
No, even if it is between 0 and 1, it will always converge, but it is not a non-linear system. Through lambda, it actually becomes non-linear. Okay?
So I miss something, because
Yeah.
since you can just approximate like xi plus xj
Right.
minus xi with a 1 minus lambda.
Right.
Okay, so it's linear.
It's non-linear.
But where is the non-linearity?
It will actually have a self-organization feature from this lambda.
Lambda is some.
Oh, yeah. So mathematicians have tried to solve this actually. Analytically, it is not solvable.
Okay.
Now, if I,
Sorry.
yes, sorry,
So this
yes.
epsilon is specific to the ij there.
Yeah, so every time step I draw it randomly from a uniform random distribution, but it's not specific. Every time it changes actually. So every time step, it changes. If I draw ij now and then again ij later on, every time the epsilon will change.
But why is there like conservation law? Like
Because-
prime
because-
plus xj prime.
Yeah, so in order to make it conservative, so if one becomes like, suppose you have 100 rupees and you are saving 10%, 10 rupees, you come up with 90 rupees. I have 1,000 rupees, I save 100 rupees and I come with 900 and we split it randomly. And it can be any fraction between 0 and 1. So if you take 400, I'll take 500, or you take something like that.
I thought that it would be a sum over all xi's, which should be conserved.
Yeah, but at
Why is
every
there a pairwise conservation?
pairwise conservation, because it's just an exchange of money. Whenever I'm trading, either some money goes from my pocket to yours or your pocket to mine, right? So there is stepwise conservation.
There could be tripartite.
There could be, but all can be, reduced to bipartite, right? I can always reduce these to two equations. Like first I change with her, and then you change with him. Okay, I can get to even in other dimensions and larger things, but it's easiest and simplest. Yes. Yeah.
What about the history of the system? For example,
So at present, we don't consider it has any memory, right? That's what he was telling, that you normally have patterns and all. We ignore. So we just say that you take two people randomly and you make them random splitting. Okay.
how can we talk about equivalence to, let's say, hierarchy of power, which is why
Yeah. So at present, I'm not bringing all those complicated features. I think of the simplest one and very idealized one where everything is happening randomly. Okay. And let's proceed, and then I'll tell you what happened. Yeah.
Why is it non-linear?
No.
Linear in x.
This is linear in x, but what will happen is through this lambda, it will become,
Only if lambda depends on x. Yes. Otherwise, it's impossible by definition.
right. So what will happen is we'll show that there is a correlation between lambda and x actually.
Having correlation and having relation are different things.
Right.
Is lambda functionally dependent?
No, not right.
At this point, it is really linear.
It is at this point linear. Yeah. Yeah. But then I will show that we can make it
But
like
perhaps
that.
it's non-linear because when you draw, it's not exactly that, right? You have a uniform distribution.
Distribution of lambda.
Xi plus xj. So it's not exactly xi plus xj, it's a random noise that you throw, and perhaps there it will not be.
But by definition, this
It is linear.
It's
Yeah.
linear.
Okay. Now what happens is all of these have exponential tails. But I talked about the Pareto law. How do I get that? As soon as you make this dependent on an agent, and this lambda I is broadly drawn from a random distribution between 0 and 1, you will find that you will get a Pareto tail. And this is as if like you have a huge system and that is broken up into smaller systems. So I have a huge system and that is broken up into smaller subsystems. Each one has a different lambda, okay? Now, each one of these lambdas would give you a gamma distribution, but then the convolution of that will give rise to the tail.
So just one
Yes.
final thing
Yes,
to clarify.
sure.
How people meet each other?
It's randomly, pure randomness.
So you have n agent and one divide by n, you choose one, and one divide by
Sure,
n.
yeah. So to come to equilibrium, it will take at least n now. Now, this is where I was telling. Now, if you check, you will find, these all have different lambdas, and you get a Pareto tail. And if you find which are the people who are in the Pareto tail, you will find that those are the ones which have very high lambda. And so it's seen that there is a relation between, your savings and the average wealth you have. So the mechanism that we are showing is that you have an economy model which can be, similar to a gas model, and both of them have a same, distribution of energy, except the temperature in the gas model is a real thing, and here it is effective temperature. Here this is the integral dimension, and here it's a parameter which can be function to this lambda. Okay. Now, if I want to derive this, the traditional way is we write of entropy functional, and then we try to maximize that entropy. And you can show that for this conservation of probability and wealth, you will get this distribution, which I actually wrote here. Now, when I have a big system composed of several systems, and each one of them have a separate lambda, then what I'm doing is actually have a functional entropy, and I'm trying to find the aggregate density, and I draw this lambda from a uniform distribution, which in terms of n becomes like this, and you can show using saddle point approximation that you will get these Pareto tails. Okay, so this is a very general mechanism which is not only found in wealth distribution but several other physics models wherever you have some quantity being exchanged. And we published this in Physical Review Letters, where I can tell you that if you give me a form of this distribution of these subsystems with certain lambdas, I can tell you what the form of the final energy distribution will be. Now, that's the question which Devojit was asking, can we model humans as just atoms colliding? Now, even though I told you, a bottle of water has 10 to the power of 23 molecules, I do not actually have to solve 10 to the power of 23 equations to say something about this bottle of water. Okay, and that's what normally we study in thermodynamics or statistical physics. You can tell a lot of things about the average properties. So the pressure in this room, for example, is the average force with which the molecules hit the walls. Now, so you have heard about this equation of state. Similarly, what we are saying that, we do not have to look into the individual details of these, but you can still say something about the economy. Now, are they so random? No. So agents have this utility functions which they try to maximize. And so two of my colleagues, I think they tried to actually formulate a model where they have n agents producing a perishable commodity. Each of them have a Cobb-Douglas form of utility function which they try to maximize. And then using this typical utility maximization and market price mechanism with market clearing equations, they arrive at the same equations, and they show that the entropy maximization in physics, which we were using to derive this law, is equivalent to utility maximization in economics. So you can actually have, a market with commodities and people exchanging or selling those commodities, and then you can explain that this mechanism gives.
But this is only under the assumptions that you have a Cobb plus utility.
Yes, but
Only in case of two commodities.
only, two agents. Very simple model of market,
So
but
I think this result is also related to fairness. So I think before 2000, in networks, there was also this question about how to design fairness and so on. And
Okay.
they proved something pretty similar to that.
yeah. So there were some Italian economists, actually, Benatti et al. They have been modeling that. There has been a mathematician, John Angle, in US, sociologist. So there was a literature in maths and economics. Yes, Sasita.
So, when we see something like entropy maximization,
Yeah.
we essentially mean that you're maximizing a single function of whole system.
Right.
But in economics, it's not.
Right. So you are doing the utility maximization of individuals, but on the whole, there is also you will see a self-organization or whatever. Okay. Now, one thing that comes out of this model is, as the lambda increases, the inequality in the distribution goes down. Okay. And so if you actually know the form of the distribution, you can calculate the Gini index for any known distribution, and this is how it would vary as a function of lambda. Now, what do we see in data? So we have Gini indices of all the countries. We also have the gross domestic savings of all the countries. And so if I run basically just a regression, Gini index versus savings, we see that there is actually a decrease in inequality whenever there is increase in savings. Now, let me remind you, this is for the smaller economies or closed economies, because that's what we are assuming. And we found that it doesn't hold if you include US, UK, Japan, which are huge economies. But for many countries in the European Union and in small countries like Hong Kong, Luxembourg, you do see something like that. Okay, you can also check. Suppose I have the Gini index, which is a function of time. Every country is thing. And I look at the gross domestic savings. So this is for Slovenia, this is for Czechoslovakia. You again find a negative correlation. Okay, so now we're not saying that this is the model which would explain the working of the economy, but maybe this is a very simple model which can capture features of this. Okay, so this is one type of model I wanted to show. The second one is on competitive resource allocation using game theoretical models, and which you are more familiar. Now, we've done actually a lot of work on competitive resource allocation using agent-based models, and we have physics reports review, which is available on my website. Now, this is a cartoon which actually tells you it doesn't matter how many resources you have. If you don't know how to use them, it will never be enough. Okay, so this person would just require one ladder to actually go through, but if he doesn't know how to use it, he'll never be able to see. Now, game theory, of course, it originated in maths, and it was John von Neumann and Oscar Morgenstern who introduced it. And we have different type of games, which, of course, we have board games, card games, video games, fill games. Yeah, I see them play games in the mobile every time. Actually, they do excellently well in that. But of course, we will not consider all these games. Now, there are games of pure ability, for example, the tic-tac-toe, which we always used to play, right, when we were small, and you can actually find a perfect play. So, if you go to the thing, there is a theorem called Zermelo's theorem, that there is a perfect play for any game of pure ability. And so I would like to call two volunteers, maybe Nikita and Shrinka. Can you come here once? I want to play a game with you, which is called Jeu de bâtonnet in French. It's a game of sticks. So instead of sticks, I have improvised. I have pens, okay? So I have exactly 20 pens. And the rule is that at any time, you'd be allowed to choose 1, 2, or 3 of these, okay? And whoever is left with the last pen would lose, okay? So you're allowed to take 3 or 2 or 1. After your chance, she will do the same. And whoever is left with the last one would actually lose, okay? So you can begin, you can toss a coin to, or you can, okay, you start.
Okay, now I have to forward you.
So you've lost that. Now let me, so thank you very much. Now it's an important lesson actually. I will show you, you can work through backward induction, and because she was the first one, she should have won unless she made a mistake. So let's do a backward induction. So if I am left with the last stick, then I lose. So 1 is a losing position. That means if 2, 3, 4 are there one before, then you would be in a winning position. And then 5 would be again a losing position because I would see like 2, 3, 4. And this way you can work out 1, 5, 9, 13, 17 are the losing positions. So if you had removed 3 in the first step, she would not have been able to beat you unless you made a mistake. Okay? Now, you got it? Yeah, but if she had continued playing the right way, she would have calculated this, then she would always win because she's the first one, and if she leaves you on 17, you cannot beat her actually.
May I add something here?
Yeah.
So when we were studying game theory in college,
Right.
our professor ended with one line.
Okay.
You must not only play the game well,
Yeah.
you must play the right way.
Yeah. Right. So this is part of, this is, yeah, so this is, right. So this is, true. But this is what is called mechanism design, and I think there will be a lecture by Chakraborty and also by Shorish. No, Rai, there's from ISI, I forgot what is it. Saurav Rai. So they will talk on mechanism design. So I can design a game like this where I will always be a winner if I'm the first one to play, okay? And I can again give you several other examples where I can design games such that I will always win.
So
Yeah.
I have a question over here.
Yeah.
When you have 6 items from men,
Right.
then she has got choice to pick up either 1 or 2 or 3.
Yeah.
So if she picks up 1,
Yeah, so the thing is like this. If you have been 5, you put her in 5, then she has no. See, if she takes 2, 3, or 4, you will be always. If she takes 1, 2, or 3, you will be always left with 1. Right.
And that's what she did. She picked up 1.
Backward, yeah. Okay. Now, we won't consider these type of games as well. What we will do is we will consider games of strategic interaction where you cannot actually have this game of like pure ability. Okay. And so typically in the games of strategic interaction, you have 2 or more players, each one of them has a strategy, and a game has more than one outcome. Now let's just consider a scenario like this. Suppose we are buying and selling stocks. So ideally, when there are more buyers and a few sellers, I would get a good price. Okay, so I would like to sell when there are more buyers than number of sellers. So I would like to be in the minority. Again, the opposite would happen. So if I'm wanting to buy, I would like large supply, so the number of sellers are larger, number of buyers are fewer. So I would like to be in the minority. Now let me give you a cartoon actually, which actually shows you what goes on in a stock market. So I've got a stock here that could really excel, sell. Everybody starts doing that. And then somebody says, oh, this is madness, I can't take any more, goodbye, buy, and then everybody starts buying. So you often see what is called herding behavior in economics, which you all are familiar with. And this is basically irrational behavior. And so, there's a famous quotation by Sir Isaac Newton who, said, I can calculate the motions of heavenly bodies, but not the madness of people. So he formulated the gravitation law, but he lost 20,000 pounds in the South Sea bubble in 1720. And so he said that I cannot model the irrationality actually. It's very difficult to model irrational behavior. Now, the way we can incorporate such irrationality in game theoretical models is using bounded rationality, and which requires you will be violating any of these things which are true for a perfect rational game. Now, in economics, normally what happens is you take something which is an equilibrium game theory, and you always have a representative agent. Here you can also incorporate heterogeneous agents with different type of strategies and capabilities. Okay, so these models actually allow you to do that. So I will talk about what is called the basic minority game, which was formulated by one of my colleagues in École Centrale, Damien Chalet, and his supervisor, Yicheng Zhang. And it says that suppose I have an odd number of players, and we would have a choice of performing either one action or the other, like buying or selling, or going to some place or not going to some place. And the minority game would win. Okay, and all of us share a finite amount of public information, and it is limited. Even if I give you a huge amount of information, because of your bounded rationality, you can remember or process only a certain amount, and that's what we call the memory. Okay, so this was inspired by L. Farol bar problem, formulated by Brian Arthur, and this was a bar which was in front of Santa Fe Institute in New Mexico. Now, we can play this game actually. So, thing like this. Every time I clap, you can either put your hand up or your hand down, and then we will count, the minority, and whoever is in the minority will win. Can we play this game a few times? Okay. If you don't mind putting your hand up, or too lazy, then put your hand down. Okay. So, shall we start? So very few hands up, so you are in the winner. Okay. So those who kept their hands down lost. Okay. So it's as simple a game. Now, I can do it a few times, or I can actually simulate this so you understand the game, right? It's as simple as that. Now, of course, what happens is my number of winners at any time can be only n-1 by 2, and that's why to have a clear winner, I take n as odd. Okay. By the way, Sasidevan did his PhD on this sort of topics, right? Your PhD was a part of it. So he's an expert on this theory. Okay. So now, what we do is, what I say is that, those who won, the group which won, this information is given. So last time 0 won, previous that 1 won, previous day 0 won, and I give you a history. Okay. But your memory is limited, so you can remember only the last 2 digits. Now, if I tell you that what could be the possibilities in the last 2 days, it could be either 0, 0, 0, 1, 1, 0, 1, 1, right? So this is the possible history. Now, suppose I have to decide on that information. One could be, I don't care what happens, today I will choose 0. Okay, so that is one possibility, right? The other possibility could be, I don't care, I will always choose 1. And this way you can see that there are 16 strategies. Okay, depending on what your history is, these are your strategy space. Okay, and if you choose, the signal is 1, 0, so which means this, and you choose strategy 7, that means you will be choosing 1. Okay, so your response will be 1.
I'm a bit lost.
Yeah.
So at time T,
Yeah.
you only remember the 2 last rounds.
Last 2 draws, yeah. So you will be given this, suppose 1, 0 is the winner. So that means this is the signal. Okay, but I could have different strategies, right? So if I chose strategy 1, I would respond with a 0. If I choose 16, then I would respond with a 1. If I have strategy 7, I'll choose with 1. Okay, is it clear? Fine. Now, suppose we play a game, just 3 players, and each one, I just give 2 strategies randomly out of this 16. I can give all 16, but I can give each strategy just 2, each player only 2 strategies. So what I do, I give player 1 this, player 2 this, and player 3 this. Okay, so you have to play from your pool of strategies. Okay, so you can just choose them randomly, or you can choose the best one, which you think is the best. So let's play this game. So what happens is I have this signal 1, 0. I can remember only the last 2 digits. So player 1 plays this, player 2 plays this, and player 3 plays this, and then I count. So there are 2 zeros and a 1, 1. So this one wins. Okay. You understand? And that's what we were doing. We were just clapping, and when I was clapping, you were putting your hands up or hand down, which is like equivalent to 1 or 0. Okay? And with some strategy, you would be able to think that, okay, if last time 1 won and before that 0 won and what so forth, what would I do now? And you would be responding with such strategy. Okay? Or you could simply toss a coin and decide what to do. And that's what happens, okay? So here, these players win, and then, this signal changes and 0, 1 becomes a thing, and you continue this game. Now, if you typically simulate this in a computer, so I have done for 5,000 time steps with 801 players, memory is 6, and 10 strategies to each player, then you will see that the, number of winners fluctuate. Okay, and each player I can give a 1 point for winning and -1 for losing, and then I can see how they perform. Okay, and you'll see that if you land up with a bad pool of strategies, it is very difficult to beat a player who has. Performance is the number of times you're winning actually. So every time you win, you get a +1. These are for different agents, and I've just chosen some randomly, and the best one and the worst one. Okay. Now, what you can do is actually you can compare it with just a coin tossing, and here there is a lot of physics behind that, which is called spin glass theory, and I'm skipping that part, but you can show analytically that sometimes just to play randomly is a better choice than if you're given a huge pool of strategies. So if you're given a huge pool of strategies, to learn and find out which strategy is the best is very difficult. Okay, so for a typical ratio or number of strategies, you can show that sometimes that just playing randomly is better. Okay, yes.
What is your mechanism at each time to choose a strategy?
You can do it like you can score your strategies and choose the best one. So every time you win with a certain strategy, you update the strategy, or you can have your own mechanism. Okay. By the way, we did some of these.
How it's related to Nash equilibrium? So there is no relation.
There is no relation. It's very difficult to find a Nash equilibrium for such things.
Except you have to do the dynamic programming equation.
Yes. Yes. Now
What happens if everyone chooses the same strategy?
Yeah. So then that you reach a Nash equilibrium. Everybody loses except one. Somebody will choose something. Now we also implement this experimentally in our JNU, actually, along with Sujay Chakraborty, who is an experimental economist. We gave these strategies to players and we made them play. And then you will find that, human beings are slightly more complicated than this, but they start, figuring out. So we actually formulated a model which is called Kolkata Pice Restaurant, and Sasidevan had worked on that. And that is a slightly more complicated in a sense. Here you have only 2 choices, so 2 resources. There you have n choices. So n resources, and then each of them compete for the resources. Okay. Now, often in game theory, you will find that you can adapt. So we introduced a sort of an adaptation mechanism. So where you play this game and you observe for tau period, and then you examine your performance. And after that tau period, what you can do is you can create 2 new strategies from your existing pool of strategies using genetic algorithm. Okay. So how does the genetic algorithm work? Normally you have 2 genes. You choose a breaking point and then you exchange the genetic material. Similarly, here I have 2 strategies, which are, these things. You choose a breaking point and then you exchange the material and you will get 2 new strategies. Okay? So that is a genetic crossover. Now, there are 2 wonderful books by John Holland and D. Goldberg, which give you a lot of things on genetic algorithms. Yes? Sure.
This is just basically a new strategy, right?
Yeah.
You may say the strategy, but you said adaptability, which is a different thing from that.
That's right. So I'm now complicating.
Differentiating because are you using them interchangeably?
No. What I'm doing is I'm now making the game more complicated.
Yeah, but
Yeah.
you just are using the term adaptability for
Yeah. So what you do is, right. So you can have your pool of strategies, but then you can cross them and create new strategies. So I allow this. Yeah, that's a mixed strategy. Yeah. Now what we find is as soon as you allow these players to adapt, you will find suddenly there will be changes in the performance. Okay. So this is the basic minority game where there is no adaptation, and here you suddenly allow players to adapt, and so you'll find that here n fluctuates, and normally it's a Gaussian distribution, and I would ideally like the number of winners to be near n-1 by 2. Okay, so if I have for example, 101, I could split as 1 and 100, and there would be 1 winner and 100 losers, or I could be 50 and 51, where there are 50 winners and 51 losers. Okay, now ideally, this would be better because you have a larger number of winners, and so you will often find that the system starts learning and converging. Okay, and then you can use several strategies, ways of adapting. For example, here we use 1-point genetic crossover with the parents being replaced by the children. Another one, we take the 2 worst strategies and replace it by the children. Then there is hybridized genetic crossover, so you take the 2 best strategies and then cross, and the same type of thing. And you will find that in 4 cases, you will get this system adaptation. And this D with the hybridized genetic crossover, where the 2 worst strategies are being replaced by the children, this works best. Okay. You can also, create things like, for example, here, after every 1,000 steps, we were taking the worst one and making him adapt. But we found that as soon as he starts adapting, he starts winning. Or here we said that, okay, 10 of the players play with hybridized genetic crossover, some play only the basic minority game. Then you'll find that there is stiff competition among them, but they perform much better to the others. Similarly, here we say there are some hybridized genetic crossover, some play 1-point genetic crossover, some play basic minority game, and you will find that at the start, when you start adapting, these start performing much better. Okay, so we gave sort of a mechanism where you can use this genetic crossover thing to gain theoretical models, and you can use it for different applications in resource allocation, as well as studying evolution of species, etc. Yes, Alexander.
Just more practical questions.
Right.
I guess the goal is that you have, as you said, n-1 winner in average.
Right. Yeah.
And if the thing is, I don't see an application. So one application would be you have an antenna in a complex network, you are sharing Wi-Fi, and you just have a protocol saying that you use this algorithm, and sometimes you will win this guy or you will lose. But this is just a decentralized. So in which case, because it seems that you are using practical learning strategy and hope that agent will use it.
Right.
But in which context it makes sense, right?
Right. So initially this was done for, choosing restaurants, for example. Yeah. So we formulated what is called the Kolkata Best Restaurant and all that. Now, what you can do is, you see that here I was telling that you wait for a period tau, which is the learning period, and only n fraction adapt. Okay. Now everybody starts adapting, nothing changes. If you take too long time to adapt, it's very bad. If you take too short also, there is too. So you have an optimal tau, you have an optimal n, and you have a k, which is the number of strategies, you have a memory m. So overall, it is very complicated.
So it's like you are saying that, assuming that you're n agents,
yeah,
and you say, follow this protocol,
yeah,
and you will win, I don't know, this many times, and you should follow this protocol.
That's right.
Is it the kind of result that you want?
That's the type of thinking. To actually pinpoint and tell that this will work the best is very difficult, because all these parameters have to be optimized. So I showed you that k, the m, and all these will matter. Okay.
Can you tell a bit more on that restaurant example that you're referring to?
Right. So maybe that I'll take up during discussion, because I've just finished my time. Okay. So we'll have discussion period in the evening and thing, and you have all these questions and much more. We can generate a thing, right? These are the references. I have 2 back-to-back articles in quantitative finance. You can find all this in my Google web page or in my web page in the university. So if you have questions, I'll take them during the discussion. And thank you for your attention.